Hi everyone, I'm Eduardo Barrios from the Facultad de Química UNAM, and I will moderate the session. Welcome to the second session of the conference, and this session will start with Thomas Stegmann from the Instituto de Ciencias Físicas UNAM from Cuernavaca, Mexico. And if you have any question for the speaker, you can raise your hand, and then well, I will give you the word. And Thomas, the floor is yours.
Okay, thank you, Eduardo. Thank you very much for the nice introduction and for the opportunity to present here or results on the steering of current flow in twisted bilayer graphene. So let us start first with the acknowledgements, because sometimes I forget them at the end of the talk, so I decided to start with the acknowledgements to thank all these co-authors of this work, which who are Jesus Sanchez, a master student, Jonathan Betancourt, a postdoc in my group, and Montserrat Navarro, student of Eduardo, and Eduardo, the chairman, who's a co-author of this work, and at the Facultad de Química of the UNAM. And of course, I acknowledge the funding of this work here from UNAM and CONACYT. Okay, then, let us start. Let us start slowly. So with graphene. So graphene, I expect that everyone knows that graphene is a monolayer of carbon atoms with lots of interesting features. One of them, I'm sorry for that. One of them is that graphene has a linear dispersion relation, which makes the electron behave in graphene as massless relativistic fermions. And one other interesting property is that these Dirac cones, they are located here at the edges of the hexagon in the Brillouin zone, and two of these cones are inequivalent, and these two cones can be interpreted here as a valley spin. So in graphene, the electrons, apart from the real spin, have a valley spin, which we denote here by K plus and K minus, the two different positions here of the cones in K space. And just to mention one of the numerous outstanding properties of graphene, which certainly everyone knows here. Yesterday evening, I checked here the number of publications with the keyword containing the keyword graphene here as a function of the year of publication. And you can still see there are about 50,000 publications per year containing the keyword graphene. So there's still big hype of research. And this drop here, this is 2021. So in 2021, we have the 11th of January, we have about already 2,000 publications with the keyword of graphene. So nobody is capable to follow this, to follow all these papers. Okay, today this talk is not on monolayer graphene, but on bilayer graphene. So the system which we consider is that we have one sheet of graphene and we place here another sheet of graphene on top of the first sheet. So we go in this sense one step back again towards graphite, which is a step of various now you can see again my screen, right? Stack of various sheets of graphene. Okay, when you stack these two layers on top of each other, you have several possibilities to stack them. One of them is here the AB stacking. So in black here, you see the previous graphene sheet, and these little red atoms, they are also carbon atoms, but now this is the second sheet. And this stacking, which you see here, this is the so-called AB stacking, where carbon atoms are here centered in the middle here of this hexagon on the bottom layer. And yeah, AB stacking, because here these atoms here on the bottom layer, let's say, belong to sublattice A, and on the top layer they belong to sublattice B. And in this case, we observe, instead of Dirac cones, we observe parabolic dispersion without a gap, as you can see here. Another possibility of stacking these two graphene layers is to use this AA stacking, where yeah, the two layers are exactly on top of each other. And in this case, we observe here dispersion, which is made of two shifted Dirac cones. However, this, as you may imagine, this solution is energetically much less stable than this AB stacking. Okay, as the title of the talk announced, we will consider here twisted bilayer graphene. So these two layers, they are not aligned as in the previous transparency. We will introduce a twist between the two layers. And when you do so, the following happens. So you have here, yeah, the video is working. You see, when we introduce a twist, the first thing which we notice is that we generate here a Moiré interference pattern. So you see here these regions of AA stacking. These generate here this interesting pattern. And yeah, you also see that the larger the twist angle gets, the smaller this interference pattern becomes. And vice versa, the lower the twist angle is, the larger this interference pattern gets here. So you see here these white dots indicating the regions of AA stacking. They are quite far away, but when we increase here the twist between the two layers, then they get closer. So this is one important observation, that we have here this Moiré interference pattern, where we have here regions of AA stacking, and in between, of course, we have AB or BA stacking symmetry between the atoms. So the simplified version is here to the top right. So we have zones of AA stacking, and in between we have these zones of AB and BA stacking. So this is the geometrical observation of what will happen in twisted bilayer graphene. Let's discuss some experimental results. So the people did experiments with this twisted bilayer graphene, and surprisingly, at some certain angles called magic angles, they observe some very interesting properties. For example, here they measure the resistance of a device made here of twisted bilayer graphene as a function of temperature. And they observe that below critical temperature, the resistance goes to 0, which indicates nothing but superconductivity in the device at certain twist angles. Here, another, from the same paper, another figure, where they studied here the resistance here as a color shading as a function of the temperature and the carrier density in the device. And they detect regions here where the system behaves as a superconductor. This means 0 resistance. And there are other regions, this one here, this red one, where the device acts as a mod insulator. And yeah, here again, some years later, 1 year later, another experiment, temperature versus carrier density, and there you observe a very interesting spectrum of regions where the system behaves as a superconductor. This is the SC, and a correlated state indicated here by these CS regions, these red CS regions, and flanked here by bulk insulating states. These are here very left and very right. So in short, what we observe here are correlation effects at certain magic angles. Yeah, to understand these effects, which caused many research in recent years, yeah, one has to take a look here at the band structure of twisted bilayer graphene, or the first step to understand these effects is to have a look at the band structure of twisted bilayer graphene here as a function of the twist angle. So what we do here is we decrease the twist angle between the between the bottom and top layer. And as I said before, what you can see here in the top row is that this Moiré pattern, the unit cell of the Moiré pattern, becomes larger and larger. As you see here, the distance between the atoms, or the figures here become more, show a larger number of atoms. What you can see here in the band structure is that the bands get flattened. When we see here, when we compare here about 9 degrees twist angle to about 4 degrees of twist angle, and you see here that these features here, they get flattened, they go to, or in other words, they go to lower energies. You see here these features, which here are about 1 electron volts, they go here to about 0.3 electron volts. Note here that they change here the scale. Here we have a scale about 1.5 electron volts, and here we have a scale of 0.4 electron volts. And when we decrease even more the twist angle, we see that these features here, they go to lower and lower energies, producing here these flat bands. And flat bands, in other words, mean that you have a very high density of states here in these regions, so you can have very high electron densities here in these regions, and this I hope make for you reasonable that you can observe their correlations effects, or that it may be possible to observe in these regions of flat bands correlation effects. Yeah, to understand further this appearance of flat bands, let us discuss here this figure showing here the Brillouin zone of the two layers. So this black hexagon shows here, let's say, the Brillouin zone of the bottom layer, and the gray dashed hexagon, this is the Brillouin zone of the top layer. And they are twisted by an angle, a finite angle. And in this way, this twist generates here a separation of the two cones. So this finite twist generates here a separation of the two Dirac cones. And generating also here this mini Brillouin zone, this small red hexagon indicating here, where we have here these two K points of the bottom and top layer around the plus valley. And here at the bottom, these are the K points at the top and bottom layer around the minus valley. And yeah, these two shifted Dirac cones, this is the approximation that we won't have any interaction between the layers. And when we switch on the interaction between the layers, what you observe is, depending on the strength of interaction and on the twist angle, you observe that these bands here, they get flattened and giving rise to these correlation effects. Okay. So far, a very short introduction into the effects which take place in twisted bilayer graphene, the most the effects which are discussed most in literature. In the following, we will address the current flow in twisted bilayer graphene, And to say it first very clearly, above angles, above these magic angles. So the physics which we discuss in the following is not related to correlated electron states. We will use in the following a single electron picture to describe the system above the magic angle. And yeah, the system which we will consider in the following is depicted here. So we have two graphene layers, and the top layer is twisted with a finite angle compared to the bottom layer, giving rise to this Moiré pattern here in the bilayer region. We will have then four contacts. We will have at the bottom layer, we will have a source contact where we will inject the electron current. And in the top layer, we have three contacts. We will have there three drain contacts. One drain contact here with arrow up, indicating here the contacts at the top edge. The down arrow indicating here the contact at the bottom edge, and the right arrow is here the contact at the right edge of the top layer. I have to point out that the layer size is about 100 × 80 nanometers, leading to a bilayer region of 60 × 60 nanometers. So this figure here, where you can see individual atoms, is just to depict the system which we are investigating. I think in total we have about 1 million, 2 million carbon atoms in the system which we are studying here. Okay, technically we use Green's function method to calculate the current flow, and as the name says, this is related to the calculation of Green's functions. Here is a single particle Green's function of the system, which is essentially here the inverse of this sum of these matrices. E is the electron energy, so the energy of the electrons which we inject here at source. H is the tight binding Hamiltonian, which models here the twisted bilayer system. And here, these sum over these sigmas, these sigma p, these are the self-energy representing these four contacts. So the sum here goes over these four contacts which we have in the system. And they take into account here the effect on the contacts on the nanosystem, on the bilayer graphene device. The tight binding Hamiltonian is composed of three parts. We have here this bottom and top layer Hamiltonian. This is just graphene Hamiltonian with interaction to first nearest neighbors, typical graphene Hamiltonian. Here the interlayer Hamiltonian. Well, there we have these hopping matrix elements between orbitals on position n of the bottom layer and m of the top layer. And these hopping matrix elements, they are given here by these Slater-Coster parameters, where we have here contributions here from the sigma bonds of the p orbitals at position n and m of the bottom and top layer, and pi bonds here of the p orbitals. And this is the Hamiltonian which we are using. For the self-energies, we use the so-called wideband model, which in other words represents a contact with a constant surface density of states. So the contact which is connected to the graphene device has a constant energy independent surface density of states. This is the general assumption of this wideband model, one of the most simple and most general model for contacts. Okay, so far the techniques which we will apply. Having here the Green's function, we can calculate here the transmission between contact I and J, let's say here the source and one of these drain contacts. So we have to calculate here this matrix product. Gamma is here essentially the imaginary part of the solve energy. So we have to calculate here this matrix product and afterwards this trace. And this is a transmission between pairs of contacts. And we can also calculate here the local current flow in the device here by this elements, matrix elements here of this matrix products and yeah, the imaginary part. This typical Green's function method, which we apply here. Let's discuss the result. Here we have the current flow in the different layers without any twist. So we go back one step to a bilayer graphene device in AB stacking symmetry. So this is a starting point with zero twist angle. And the red color shading, this is the current density. So very high red is the maximum current and white is zero current. And here we have the current in the bottom and the top layer. And yeah, what we can see here is it's the current injected here at the left edge of the system by the source contact, goes almost parallel here to the confining boundaries, and then it hits here the bilayer region and interchanges between the two regions and giving rise here to this current which we observe here, which then finally ends here at the right edge, mainly ends here at the right edge of the top layer. Now, there are some currents deviated here to the bottom and top edge of this top layer here. And yeah, but essentially the current goes here from the source contact to this red bar here, to this contact D right arrow. And you can see here it's a right, this is the interlayer current. So a red color shading indicates here a current which goes up from the bottom layer to the top layer, while a blue shaded regions indicate here a current that goes from the top layer to the bottom layer. So you see here there are oscillations in the bilayer region between the top and the bottom layer. But eventually all the current, or essentially the most part of the current, goes here straight through the device. This is observed here without any twist. We repeat these calculations for the case of a finite twist, here 2.9 degrees. So again, above the magic angle. And what we observe here is that the main part of the current is deviated here to the top edge of the top layer. Now we see here that the current which is injected here, finally, the most part goes here to the top edge of the top layer. There are some parts which pass straight through the device, and there is a part which goes here to the bottom edge. But you clearly see here the difference, that a larger fraction of the part goes here to the top edge than here to the bottom edge of the top layer. And yeah, again, in the interlayer current, we see here strong oscillations between the two layers. And yeah, so this is one of the properties of findings, which I will discuss in the remaining part of the talk, is that for a finite twist angle, we observe here that a certain part of the current is deviated or steered towards one of the lateral edges of the system. Here in this case, for the positive twist angle, we see here that a larger fraction of the current goes here to the top edge. And yeah, we can, this steering of the current, we can manipulate the steering of the current here by going to a negative twist angle. In this case, we see here that a larger fraction of the current goes to the bottom edge. For negative twist, we have here the larger current to the bottom edge. For a positive twist, we see that the larger fraction of the current goes to the top edge. And so the steering of the current can be controlled by the sign of the twist angle. Moreover, we can also change here the electron energy. Now we can go here. This is for electrons which are in the conduction band, which when we inject the electrons here in the valence band, we see here that instead of going to the top edge, the electrons go mainly to the bottom edge. So the steering can not only be controlled by the sign of the twist angle, it can be controlled also by the electron energy, which is accessible through electrostatic gating. Okay, yeah. Let us quantify a bit these results. So we were just discussing here figures of the local current flow. I hope you agree that there is an obvious asymmetry between the current flow here to the top edge and the bottom edge, but it might not be that clear that the larger fraction, yes, is deviated here to the top edge. So to quantify our results, we measure here the or we have calculated here the normalized transmission as a function of the twist angle. And so the blue curve here, this is a transmission which goes from source to this contact here, to this drain contact, these blue bars. The green curve to this green bars, the red curve to this red bar. And here we clearly see for a twist angle about 3 degrees here, we see clearly that a larger fraction of the current, a much larger fraction of the current is deviated, is steered towards the top edge, while less current goes here to the bottom edge. This is here the green curve, or to the edge here at the right end of the system. This is the red curve. So we clearly see here an asymmetry of the current flow towards the top edge for a positive twist angle, and for negative twist angle the situation is reversed. For negative twist angle, you see here that the larger fraction of the current goes here to the bottom edge of the top layer. So this figure is here to quantify our findings, and yeah, this steering of the current flow, in consequence, leads to a finite non-local Hall resistance. Here we have the here we have measured the longitudinal and the Hall resistance of the device as a function of the electron energy. And what you see here, which is proportional to the electron density in the device. And what you can see here is that the here in a broad regime of electron energies, we see here a finite non-local Hall resistance. This red curve is this Rxy, generated due to this steering of the current flow, and which should be measurable in experiments. And the gray curve here at the background is the density of states, which somehow resembles here this Hall resistance, the shape here of the Hall resistance. And yeah, we have quantified our results even more here. This figure shows these normalized transmissions as a function of the electron energy and the twist angle. And you see here these red regions, these broad red regions. These indicate the regions where this steering of the current flow appears. So here we see that for positive electron energy at a positive twist angle, the main fraction of the current is deviated towards the top edge contact, while we can change the situation here by changing the twist angle, going here to the and the electron energy, we still go to the top contact. When we change only here the twist angle, we go to the bottom contact. This is this figure here, and So we have this steering in broad regions of experimentally accessible parameters. And again, it can be controlled by means of the sign of the twist angle and the electron energy. This means by electrostatic gating. Okay, now we are somehow left to understand this behavior. And to do so, yeah, we have to take a look again at the band structure of the system, which is shown here for the twist angle of 2.9 degree. And here, these figures, these are the isolines, the energy isolines of this band structure here. It's these two energies of this black horizontal line, which is about 0.3 electron volt, and this dashed horizontal line, which is about 0.135 milli-electron volts. And for these energies, these are the energy isolines of the band structure. So here is a function kx, ky. And what we observe here is that for at 270 milli-electron volts, so the black horizontal line, we have here these trigonal energy contours. We have here this trigonal energy contours centered here in the middle of the Brillouin zone of the twisted bilayer graphene device. And yeah, these orientation of these triangles switch when we go from the K plus valley to the K minus valley. And they are these trigonal shaped energy contours. They are the one of the essential ingredients to understand the steering of the current flow. You can do so by using the so-called kinematical construction, which is the following. So we have here in red, this red hexagon. This is the Brillouin zone of the twisted bilayer graphene device. And this point here, this is the K plus point of the bottom layer. And there we have drawn the energy contour of the monolayer graphene where we inject the current. So we inject the current in the region of monolayer graphene. And this is this energy isoline here. This blue triangle, this is the energy isoline in the bilayer region. And it's the same energy. This orange arrow here, this indicates the injected electron beam. So this orange arrow has to be perpendicular to the energy isolines. So it indicates the group velocity of the injected electrons. And this black line here connects this black line having an inclination of theta. Theta here is the angle of the twist angle. This connects here the Brillouin zone, or this connects here the energy contour in the monolayer region with the energy contour in the bilayer region. And the intersection point here of this black line with the energy contour in the bilayer region, this defines here the group velocity in the twisted bilayer region, the group velocity of the electrons in the twisted bilayer regions, which points here upwards. The arrows have to be again perpendicular on the energy contours, and you see here in this case, these arrows, they are turned upwards. Here we have an arrow approximately horizontal, having an inclination here of 3 degrees, but approximately horizontal, yielding here a vector which is turned upwards. When we repeat the same analysis around the minus valley, of the bottom layer, we see here that the same arrow, is partially turned downwards here, but the intersection point is more here in this edge of the energy contour. So you can see here that also part of the current is going here upwards. This black, I forgot to tell that this gray shaded region here, represents the dispersion of the electron beam. So because the injected electron beam shows a finite dispersion, and to take this into account here in this classical picture of electrons, we take here, consider here this rectangular gray shaded regions, and all the intersection points here of this gray rectangular with the energy contour led to small arrows, indicating that all the current here injected is steered here towards the top edge of the system. While here, for the K- valley, you see here, the intersection points are here at the corner of the energy contour. So part of the current will go downwards and another fraction of the current here will go upwards. At the end, the current here is dispersed strongly here in this situation. So this kinematical construction predicts or confirms that a larger part of the current will be steered towards the upper edge of the system. It also predicts that the steered current will be partially valley polarized. We see here the electrons around the K+ valley, they go upwards. So electrons from the K- valley, part of them goes downwards, other part goes upwards, they get dispersed strongly. So this kinematical construction predicts that part of the current is valley polarized. Before discussing this aspect, just to show you the figures here, you can do the same analysis here at a negative twist angle, predicting that now the K- electrons from the K- valley go downwards, while the electrons from the K+ valley are dispersed strongly. So for negative valleys, not only the steering direction is reversed, also the sign of the valley will switch. We will detect at the bottom layer, at the bottom edge, we will detect electrons from the K- valley, whereas for positive angles we had at the top layer, we had at the top edge, we had electrons from the K+ valley. Okay, here we analyze the valley polarization in different regions here of the device, these purple marked regions here. And here close to the injecting source contacts, we have here the valley polarization, and you see, well, the electrons are essentially unpolarized here in this region AS, close to the source contacts. We see here that these the colors in these figures are essentially white, indicating zero valley polarization. When we measure now the polarization here in the regions A up arrow, down arrow, right arrow, we see here that as predicted by the kinematical construction here, for a positive twist angle and positive electron energies, we observe here in the region A up arrow a current which is largely polarized around the K+ valley, while for negative twist angle, positive electron energy, we see here that in the region A down arrow, we have here polarization around the K- valley. So these figures here confirm our expectation that the current which is steered towards one of the edges of the system is largely polarized around one of the two valleys, while the fraction of the current which is passing straight through the device is essentially unpolarized. The steering disappears when the trigonal energy contours disappear. This we can see here when we lower the electron energy here from about 300 milli-electron volts here to 135 milli-electron volts. We have here no longer these trigonal shaped energy contours. We get these almost circular energy contours. And in this case, the steering of the current flow essentially disappears. Shown here by these figures where the most part of the current goes straight through the device. Okay, yeah, and with this, I'm almost at the end of my talk. So the take-home message is that we observe steering of the current flow in twisted bilayer graphene, shown here very clearly for two parameters, the twist angle as well as here electron energy, where we see here in these red regions here indicate these red regions which are present here in T up arrow, but not present here at T down arrow and the same for the same parameter. They indicate that the larger fraction of the current is deviated here to the top contact. And these figures here clearly show this steering of the current flow in twisted bilayer graphene. It is explained by the trigonal shape of the energy contours and the finite twist angle of the device. This is also an important ingredient in the kinematical construction, that there is a finite twist of about 3 degrees, of some few degrees. It is not a correlated phenomena. It's a single electron phenomena, which we observe here. I showed clearly that it can be controlled by the sign of the twist angle and by the electron energy, which in turn is accessible through electric gating. And I showed that this steering of the current flow manifests in a non-local Hall resistance, a finite non-local Hall resistance, which should be measurable in various experiments. That here the Hall resistance is different from 0. And the steered current is partially valley polarized. And if you're interested in the details, you can have a look here in this paper which you can find here in the archive, but it should be out within the next week here in Journal of Physics Materials. So they accepted it I think yesterday for publications there. And with this, I thank you for your attention, and I'm looking forward for your questions.
Okay, thank you, Thomas, for the interesting talk. Well, we have a question here from Gerardo.
Hi, Thomas, very nice work, very impressive.
Thank you, Gerardo.
I have two questions. First, can you relate this steering current with the kind of Lorentz force due to a magnetic field? Because it is known that in this twisted bilayer graphene, there is an effective magnetic field, which is non-homogeneous. So I was wondering. That's my first question.
Well, I think the magnetic field which you mentioned is this pseudomagnetic field caused by the strain of the atoms due to the buckling in twisted bilayer graphene. Do I understand this correctly, or?
No, it's like because you have an electron that is moving in the other layer, so it produces a magnetic field. So there are some it's not related with the strain.
Okay.
It was related with. In fact, it is given by the curvature. Well, it depends precisely on the valley, and it's space-dependent valley momentum. That
okay, it depends. It depends on the. It's a pseudo. It is not due to the strain of the atoms, but exactly. It depends on it. But it depends on the valleys.
Yeah. So yeah. And this is a well.
I'm not aware of the details of this, but I think you are right. I think you are right that when this depends on the values, it should be that you can explain this by this magnetic field. Do you have some references on this?
Yeah, we have a paper in the archive, and we have another in Physical Review B about twisted.
Okay.
Last year. Well, I can send you. I can send you. I will send you. But my other question, because I lost my internet connection, so I was not able to see everything. Sorry. My question is that when you have the magic angles, did you study the magic angles? What did you got? Or because maybe I missed that part.
We did not. Well, we can. Let me hear this figure. Okay. Here in this figure, we can, in principle, calculate the current steering for all angles in which we are interested. So, and we observe also their current steering. For these magic angles, well, the correlation effects at the magic angles, they are not contained in this simple tight binding Hamiltonian, right?
Yeah, I know, but so, I'm not interested in that, because what is interesting that you have these flat bands, you should have localized the states that you will expect no current at all. That's why I was asking you. I mean, I know that without correlation effects, the trick is that you produce flat bands which are localized.
Yes, the flat bands, they are there. The flat bands, they are contained. You're right. But there will be the problem is a bit, there will be around zero energy, right? The flat bands. And yeah, for zero energy, the problem you see here, we have here this gap. We have calculated this steering of the current flow for electrons here for electrons with energies larger than 0.08 electron volts and lower than minus 0.08 electron volts, because for very low electron energies, the Fermi wavelength of the electrons becomes very large. And then you have the problem that the Fermi wavelengths may become larger than the twisted bilayer region, which we simulate numerically. And then our results will be affected strongly by finite size effects. So then we are in the dilemma that we have to make the device larger and larger and larger to simulate correctly the systems. So this regime we did not include here in this study. So yeah, this would be my my answer. Maybe you can. Maybe I think we have it. Let me see, where is the, I think we did it once here and the result is quite reasonable. You see here this figure, this one, oops. Here we have calculated the Hall resistance. And here you see for well, this is, I think, it's not completely correct. This is 2.9 degrees, this figure here. So it's above the magic angle. But you see here for very low electron energies, we have here this increasing longitudinal resistance indicating towards localization of the electrons towards very flat bands. You see here also we have here in the Hall resistance, we have here this dashed red line. There we did not calculate the Hall resistance for the same reasons. It's, the results will be wrong due to finite size effects.
Yeah, but it seems to be more or less in agreement with the pictures that the people have, because for these states at the magic angle, they are basically low-level lambda levels. So it's this picture seems to be in agreement with that.
Okay. Okay. Are there further?
Thank you very much. Yeah.
You're welcome, Gerardo.
Are there any other questions from the audience?
Just a simple question. So this current steering is independent of temperature? I don't see, you don't include it.
Well, independent of temperature. Well, the effect of temperature, the most important effect of temperature will be that you have some phonons around there when you go to higher temperatures, and as long as you can assume coherent phase coherent electron transport, or results will apply also for finite temperature. In other words, I believe that these results can be observed when the mean free path of the electrons is comparable to the twisted bilayer, so the size of the twisted bilayer graphene region. In other words, yes, the temperatures have to be low.
Yeah, thank you.
Another question?
You have a question, Eduardo?
Yeah, well, actually, I have one question that I think it's important to ask. How easily is to create experimental with this device? Do you have any insight about it?
Well, I think it or considering the experiments which are already published on this, where they have largely homogeneous twist angles about, in the device, where they measure very precisely these correlated states, I think there should be several devices already out there where one should have a look on this Hove resistance. You saw in these figures before of the devices. Typically, they have 4 or 6 contacts attached to the device, and from or research, I have the impression that the effect is quite robust and should be observable in devices. So yeah, for the experimentalists here in the audience, it would be great when they could have a look at just at the Hove resistance of the device.
Okay, thank you. Well, any other question? Okay, if not, we thank to Thomas, no, virtually.